3, 2, 1, 0.
Hello, old friends. Welcome to the stream. Welcome to the stream. My name is Brenden. Brem. Welcome to the stream. Let me check that my sound is working. I think it's working. Gotta verify the sound. How do I turn up the volume on my sound machine here? I don't know how to do that. How do I fix the volume? All right. I don't know how to fix the volume. Oh dear. I don't know how sound works. I think it's working. It looks like it's working. I can see the sound meter moving. I think we're good. I just can't figure out. Oh! I think I figured it out. Did I get it? No. It's not working. I don't understand why the sound doesn't work. All right, I give up. I give up with the sound. Let's see, is everything good here? I think we're all set. I think we're all set. I think the stream is good. Let's do it. Let's be on the stream. So, welcome back. My name is Brenden, or welcome for the first time. If this is your first time joining the stream, we're going through this book here. It's called Cracking the Coding Interview. We are doing the problems out of this book. Why are we doing this? I started doing this as a way to learn Rust. I figured, why not? Why not practice these problems while also learning Rust? If you've worked in tech at all, in computers, then you have probably, without a doubt, encountered these types of problems, these cracking the coding interview type problems. They're not really a lot of fun to do, but it's just kind of a necessity if you want to get a computer job. Yeah? So we're going through these problems and we're answering them. Now, recently, I think 2 weeks ago, I started doing a review of what's happening in Rust at the start of the stream. So let's start there. Let's look at this week in Rust. So there's a blog post or blog thing, I guess. I don't know if it's a blog. What does blog mean? I don't even know. Anyway, there's a thing. It's called This Week in Rust. It's published every week, and it's basically an aggregation of a bunch of other blog posts. I guess it's like a meta blog post about what's happening in the Rust community, with the programming language, tooling, so on and so forth. So this is where I like to start, kick things off, talking about what's happened in Rust this past week. So there's lots of good stuff on the This Week in Rust this week. Let's start off with this one, which is, I think that's readable. 5 super helpful Rust things that nobody told you about. Pretty cool. And apparently they're not offering a refund if someone told you about them, but here they are. So I definitely already knew some of these, but let's review them really quick because they're pretty cool. So let's do it. Pretty print debug. So I know I personally use this debug format thing at all, where you do like : question mark. However, you can also put the octothorpe or hash symbol before the question mark. So you can do : octothorpe question mark to print something out, and it will pretty print the output like this. So that's pretty handy. All that pretty print means generally is that it will split the output into multiple lines, right? So it inserts new line, and then it adjusts the indentation depending on like what level of the data structure each item is at, and makes it a lot more readable that way. So check it out, pretty handy. All right, here's another one, which is the unimplemented macro. As it says here, sometimes you want to write code using function without having to write the entire implementation. So you can merely throw in this unimplemented macro, which expands to an expression that will compile regardless of the expected type. Yeah? Cool, pretty handy. All right, here's another one. I didn't know about this. This is a new thing. Sometimes you want to create a copy of a struct with one or more fields different. Well, you can use this, or you can do this by manually cloning and mutating the result. There's an easier way, using the ... operator in a struct literal followed by an instance of the struct will initialize the remaining fields of those to those of the instance. Conveniently, it doesn't rely on clone being implemented in the struct. Wow, that's pretty cool. So there it is. Basically, you can specify some default whatever and overload individual values, I guess. That's pretty cool. Interesting. I'm probably gonna use that. That seems handy. All right, what else? Pattern match guards. Sometimes when pattern matching, the cases you want to handle don't map exactly to the patterns of the data you're matching on. For instance, you write some code patterns like this: match XY, so this is like a tuple. And then you have like some I and some 0, none. Some I, some j, okay. I divided by j, otherwise none. Alternatively, you can combine two of the cases like this. Match XY, some ij, and then if else, cool. Yeah. However, there's a better way than either of these guards. Patterns can have a trailing conditional expression called a guard. Interesting. I did not know this one. This is a new one to me. So some I, some j. If j is not equal to 0, okay, then return some I over j. Huh. Otherwise, return none. Cool. This is pretty cool, but it does seem like something that you would very rarely use, occasionally use, thus I'm probably going to forget about it and never use it again. So try to remember it, but my brain's not that good at retaining lots of esoteric syntactic stuff. Cool. Want to left pad in Rust. So this is talking about formatting numbers, integers, for example. Want to left pad in Rust? No need for an external package. Simply use : greater than format operator followed by the length of the padding, and you'll get it. Cool. Most languages have this. By the way, this is a pretty common pattern, so that's good. Oh, did you want to pad things on the right too? No worries, just use :less than, and you can pad it. Cool. But wait, there's more. If you want to pad on both sides, we've got that too. : caret will do the trick if you tell it how wide the padded string should be. Neato. Neato. Huh, cool. You can pad it. Did someone ask you, or did someone ask if you can pad with different characters? Sure thing. Stick the character you want to pad in front of the arrow and you're all set. Wow, look at that. You can pad it any way you want. This prints out, scores, blah, blah, blah. Cool. So that's a pretty cool little blog post. Learned some things in there. What else? So this is a post about this thing called Raptor Q, which is some library for doing, I don't know, stuff, math stuff, I guess. Anyway, this is an interesting blog post just talking about how to, or how this person, who's the author here, Christopher Berner, optimized this thing, and I guess some of the work they did on making it really fast. Looks like it went from throughput of 39 megabits per second to what? Almost a gigabit, 965 megabits per second. That's a pretty big improvement. That's more than an order of magnitude. It's like 20 times. Wait, 20 times? Yeah, a little more than 20 times faster. So that's pretty cool. What else? So this post came up on Hacker News. This is about, or rather like a proposal for implementing monads in Rust. And monads are basically an abstraction that is, I don't know if it was like invented. That's maybe not the right word, but I mean, I know of it from Haskell, and I'm not really sure where it came from or like what the history of it is, but anyway, this is just talking about a proposal to put monads in Rust. So if that's interesting to you, then check it out. To me personally, I'm not sure if it's really a good idea. It's like taking the language, like the more abstract the language becomes, then the harder it is for people to actually use it. And there's a balance between more levels of indirection and more abstraction, and you know, usability, I guess. Okay, so WireGuard is like a VPN implementation, basically. And so this is a post about implementing the WireGuard protocol in Rust. So that's pretty cool. Something like a VPN service is a pretty good candidate for Rust because there is security stuff involved, right? You want your code to be safe and correct, definitely, when it comes to a VPN. So that's pretty cool. Check that out. Another post here talking about futures in Rust. And this is a pretty good blog post if you are interested in getting into this. This is part 1. I'm not sure if there's a part 2 yet. I think part 2 might not be published yet, but it's a good post by Joe Jackson. Check it out. And so this is a post about mocking in Rust with conditional compilation, which is an interesting interesting way to do it. This is kind of like a nod to C macros, and you know, this is one way to do it. I'm not sure if this is really the best way to do it, but worth thinking about at the very least. And then this is a post about using TensorFlow with Rust. It's like a face detection example. It's kind of interesting if you want to maybe mess around with TensorFlow and use Rust. Then you know, here's a starting point. All right, this post is a part of a series about domain-specific languages, DSLs in Rust. So if you find yourself maybe wanting to implement a DSL, this is worth checking out as well. Here's another post about async and Rust, popular subject, an important thing to get right. This goes in more detail about like how it's actually working underneath and so on. So talks about the current state of async and so on in Rust. What else? Yeah, this is a post just about what's going on with WebAssembly, specifically in Rust, and I'm not going to go into that in detail, but that's it. So, quick overview, what's happening in Rust right now in the past week. Let's get on with the coding. So, last week we finished up problem 4. We're on chapter 8. Chapter 8, problem 4. It's the last one we did. That was power set. So the next problem is recursive multiply. Recursive multiply. It says, let me just show the book. Recursive multiply. Write a recursive function to multiply two positive integers without using the multiply operator. You can use addition, subtraction, and bit shifting, but you should minimize the number of those operations. Okay, so the easiest way to multiply is to use addition. Right? Multiplication is just addition repeated n times. Yeah. So let's do that. Let's open up VS Code. Okay, we got VS Code. Let's start. Let's copy problem 4. Copy. Paste, and we're on problem 5. Okay, let's delete all this stuff. What are we calling this problem? This problem is called recursive multiply. Test recursive multiply. Cool. Delete this, and then let's implement our function. Function recursive multiply. So we'll do A, and this will just be an I64, and then B, I64. Whoops. And it will return an I64. All right, so so A times B is just A plus recursive multiply of A times B minus 1, like that. Right? Okay, and then if So if b is greater than 0, return that. Otherwise, sorry, this should be greater than 1. Otherwise, return a. And then if should be one more condition here. So if b is 0, if b is equal to 0, then it should just be return 0, and then else if b is greater than 1, return a plus recursive multiply a, and then b minus 1, and otherwise return a. Okay, I think that's it. Let's test. Let me restart RLS because it's broken already. All right, start equals recursive multiply 2 times 2 is equal to 4. 2 times 3, 6. 2 times 4 is equal to 8. So on and so forth. Let's try 3 times 2 is equal to 6. 3 times 3 is equal to 9. Whoops, what did I just do? 6. What happened there? 3 times 4 is equal to 12. Yeah. That's basically it. All right. Let's check it out. Cargo test. If I did everything right, this should work. Boom. Recursive multiply. Okay. Let's test the 0 case too. I didn't have that. 2 times 0 equals 0. Yeah? Beauty. Okay. Let's test one more case, which is the case of a negative number. Yeah. So how should we do that? I think I should just add one more case here and say else if b is less than 0. Yeah. If b is less than 0, then we'll do negative a times recursive multiply of a and b dot absolute value. Whoops, too many. There we go. Okay, let's test negative cert equal recursive multiply. Let's go 2 times negative 2 should be negative 4, and then negative 2 times negative 2 should be 4, and then negative 2 times 2 should be negative 4, like that. Missing. Oh dear. What did I mess up here? Oh, this should be minus 1. Yeah. Ooh. Did something wrong. Negative 2 times negative 2. Negative 2 times negative 2 should be equal to positive 4. Yeah, I still know how to do basic arithmetic. Why is that? So b is negative, yeah. So the first time through this, it will go through here. Then I'm going to negate. I'm going to negate. Hold on, I want to add a couple more cases. Just with 1, -1, -1, -1. So this should be -1, this should be 1, and this should be -1. Okay. Why does this fail? Why do... two negative numbers fail? So this should be... oh, this shouldn't be a multiply, this should be a plus. There we go. That's where I messed up. Oh, maybe not. Oh, yeah. I see. Okay, I'm totally doing this wrong. This should be like this. If... yeah, okay. Oh dear. What do I do here? So if b is less than 0, oh yeah, this should be b plus 1. Derp. Nope, still doing it wrong. So if b is less than 0, should be a... I mean, multiplying by a negative value is just, should actually just be the same. It should be like this. Absolute value of b minus 1. And then a minus that value. Yeah, this is right. Okay, but it's still blowing out. Line 26. 2 times -2 should be -4. Yeah. I think I shouldn't be subtracting that. No, that's still wrong. Oh, I see. It should be a minus a plus. Yeah. Okay. There we go. Got it. Boom. Let me just test one more case with this. It should be 1, let's do 1 times 0, should be 0. 0 times 1 should be 0. Cool. That's it. Add that. Oh, I need to add one call here in main to this function. Check that Clippy is happy. Format everything. And that's it. Problem 5 complete. All right, push that up to GitHub. Whoops. Let's look at problem 6. Problem 5, done. Let's copy that, paste, yeah. And wipe the slate clean, clean slate, blank, fresh, blank page, beauty, okay. Let's restart my VS Code to update to the latest and greatest. Beautiful. Let's go to the book. To the book. Problem 6, Chapter 8, Problem 6. This is a bit of a famous problem, one you may have heard of. It's called Towers of Hanoi. In the classic problem of the Towers of Hanoi, you have 3 towers and n disks of different sizes which can slide onto any tower. The puzzle starts with the disks sorted in ascending order of size from top to bottom. In other words, each disk sits on top of an even larger one. You have the following constraints. Only one disk can be moved at a time. A disk is slid off the top of one tower onto another tower. A disk cannot be placed on top of a smaller disk. Write a program to move the disks from the first tower to the last using stacks. Cool. So, no doubt you may have heard of this problem before. I think it's a lot easier to understand this problem if you visualize it. So let's see if there's a game that we can play. Or just look at the pictures. Let's see. Here we go. Here's an animation. Can we play this? How do we play this animation? Oh, there we go. It's a GIF. A GIF. GIF is the right way to pronounce a GIF, by the way. Am I sharing my screen? Yeah, there we go. So this is the Towers of Hanoi. How does it work? Well, you move these guys around until they're all ordered the right way. Yeah? So let's see. Move that little guy there, move that guy there, move that guy there, move that guy there, move that guy there. That guy goes there, that one there, that one there, that one there. Yeah. Let me go back to the Wikipedia page here and look at the solution, because I'm not going to try to figure this out. So, recursive solution, the key to solving a problem, yada yada. Okay. For the Towers of Hanoi, label the pegs A, B, C. Let n be the total number of disks. Let the number the disks from 1 to n. Okay. Assuming all disks are distributed in valid arrangements among 3 pegs, assuming there are m top disks in a source peg, and all the rest of the disks are larger than m, so they can be safely ignored. To move m disks from a source peg to a target peg using a spare peg without violating the rules, move m-1 disks from the source to the spare peg by the same general solving procedure. Yada, yada, yada. Okay. Move the disk m from the source peg to the target peg, which is guaranteed to be a valid move by the assumptions. Simple step. Move the m-1 disk, so we've just placed the spare peg from the spare peg to and repeat that forever. All right. And here's an illustration of that algorithm. Okay. It's basically just the same pattern over and 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 over. Okay. So the question itself says, write a program to move the disks from the first tower to the last using the stacks. Easy peasy, right? This problem, Towers of Hanoi. Okay, Towers of Hanoi. Let's implement that algorithm. Move m-1 disks from the source to the spare. So let's have a vector here. We'll say let pegs equal pegs. This will be a vector of I'm just going to use integers like 1, 2, 3, 4, 5. Yeah. Pegs equal vector. So there are going to be 3 pegs. 1, 2, 3. Actually, this can just be. This can be a vector of vectors. This can be like this. Vector, vector, 32. Whoops. Yeah? Oh wait, I need to initialize this. So vector, vector. So first I'll have a 1, 2, 3, 4, 5. This is supposed to be a stack. I'm going to reverse the order here. So it's like 5, 4, 3, 2, 1. Does it say how many I'm supposed to have? 3 towers and n disks. I'll just use 5. Right? Program to move the disks from the first tower to the last using stacks. Okay. Why did the number of spaces change? Right, weird. I don't know why the number of spaces just switched in VS Code to 2. I think the default is 4 in Rust. And that's the preferred style. Okay. So I got some pegs. Oh, this should be empty. So this is empty and this is empty. So I'm trying to move to the last. So I'm just going to say move to last peg. And then it's just going to take my pegs, which is vector, vector, right, 32. And that should really be a mutable vector, and then oh, whatever. We'll take any vector, and then I'll return a vector. Which is the new one. Fresh new moved 1. Yeah. Okay. See if that compiles. It doesn't. Oh, it's because I'm not returning anything. Okay, return the inputs to that function. There we go. All right. That compiles. What's next? So move m -1 disks. Assuming there are m top disks on a source peg, and all the rest of the disks are larger than m, so they can safely be ignored. Number of the disks. Yeah, source, target, auxiliary. What is n in this? Oh, it's saying this is the number of got it. All right, so if basically if the first peg is not empty, let's say, so if this is not empty, yeah, otherwise peg, well, we're just going to return this peg, these pegs in either case. So if pegs, so if the first one is empty, sorry, is not empty, then move to last peg. Basically, we're going to do the exact same thing here, which is going to be I need to basically update the or rather I need to remove from trying to understand how this algorithm is implemented. Move the, oh, I see. So they're flipping around these arguments here. Source, target, I see. So this last argument, this is kind of confusing the way this is done here. But I guess this also, well, this also kind of makes sense. I can't copy this pattern exactly with the way that I am implementing this, yeah, because I'm trying to just pass. I guess what I could do is just split this into, you know, split the arguments into like the 3 separate pegs. Fine, I can do that. So we'll do source. This can just be a slice I32, and then target I32, and then we'll say auxiliary I32. And then we'll say if source is empty, or sorry, if the source is not empty, move to last, source. Let me change these to vectors because I want to do stuff to them that I don't think I can do to a slice. Yeah, okay. So here I'm going to say let what are the individual disks? Let disk equal source dot pop. Right? So I'm popping the last. Just make sure pop is doing what I think. Removes the last element from the vector and returns it. Yeah, okay. So disk equals source dot pop, and then we do source, and then we're basically like flipping around the auxiliary and the target like that. Okay. And then see, the thing I don't like about this implementation is that it's like modifying these things in place, but it's not really what I want to do. So all right, let's change it. Oh, hold on. Yeah, so target dot append disk. So we add this disk to the target, and then we say move to last peg. Or move, move from auxiliary to target. Source, right? Makes sense. Okay, and then we return source, target, auxiliary. Otherwise, we just return the source, target, and auxiliary. Unwrap that guy. This needs to be mutable, expected mutable reference. What? Oh, append is not, right, this should be push disk. Sure. And then basically just copy or clone all of these. Yeah. Cannot borrow is mutable. Why can I not? Do I need to, I guess I need to explicitly tell the compiler that I want to make these mutable, right? Okay, rather than just trying to do everything in place, let me make these references. Fine. And then that makes this whole thing a little simpler. It also means I don't really need to return a vector like this. Okay, good enough. Split disk equal, and then, yeah, change these guys to mutable, whatever. I don't need to clone them. I don't need to return anything. That's it. All right. Then, move these guys to the last peg. Pegs 0. 2 pegs 1. All right, move everything from 0 to 2, with 1 being auxiliary pegs. Then, if I do assert on pegs, needs to be mutable. It should be equal to this. Basically, everything moved to the last. And these need to be mutable references. Like that. I can't do that. Let me just make these separate. 3 separate vectors. And then that will appease the the borrow checker. Okay. Source, target, auxiliary. I have to explicitly say immutable, right? Yeah. No pegs. We don't have pegs no more. We got rid of that guy. Okay, source should be an empty vector. Target should be 5, 4, 3, 2, 1, and auxiliary should be an empty vector. Yeah? Oh dear. think I messed this up. I think the push, or the... Yeah, that's fine. Nope. Still doing it wrong. What am I doing wrong here? Source is 54321. Target empty. Source from source to target. So as long as the source is not empty, okay, we're going to move to the last peg. Or rather, let's change this to move to peg, or move to target. It's more descriptive. Okay, so if the source is not empty, okay, move to target, source. I think where I'm messing up here is that what am I missing? So if the source is not empty, move from the source to the auxiliary and make target the auxiliary. Yeah, okay. And then, so I think the issue here is that I'm not passing, yeah. I need to basically pass this in value through, which value size -1. Boom. Okay. Yeah, that's it. All right, that makes sense. It's so simple, it's confusing to me. Put this in main to make the compiler happy. Cargo format, cargo test, Clippy. That's it. Towers of Hanoi. It's pretty simple. Basically doing that guy. Making that happen. All right, let's look at the next problem. Next problem in the book. Hope everyone's having a nice Saturday. It's a pretty nice day here in New York. A little chilly, but it's nice. It's sunny out. sunny day today. Okay, problem 7 is called Permutations without duplicates. It says, write a method to compute all permutations of a string of unique characters. All permutations of a string of unique characters. Right here. Show the problem. They're permutations without dupes. Write a method to compute all permutations of a string of unique characters. Okay. So, solving this seems pretty straightforward. I think the first thing to do is to solve the base case, and then the base cases, and then go out from there. This is actually very similar to the power set problem that I did last week. That was what, problem 5? Yeah. No, sorry, problem 4. Very, very similar to this problem set, I believe. Let's do it. Let's solve it. All right, problem 7. What is it called? Permutations without dupes. Test. Permutations without dupes. So, no duplicate permutations. I'm not quite sure what duplicate permutations means, but yeah, let's just do it. So, takes in a string, I guess, and it returns a string. So what are the base cases here? Write a method to compute all permutations of a string of unique characters. So it says the string is unique. And what is a permutation? That just means, I think, rearranging the letters. Yeah, probably it must be. So what are the base cases? So one is that the string is empty. Yeah. So if the string is empty, that's really easy. Just return an empty string. I don't need this return here. Okay. And then the other case is that the length of the string is equal to 1. The next case, and in that case, so we're returning all permutations, so this should actually be a vector of strings. So the length of the string is 1. This should be a vector like this. Okay. If the length of the string is 1, then I'm basically going to return a vector of, or rather, we're going to return this of basically an empty string, or rather permutation without dupes of s. We'll just say, does that make sense? Can I take a slice of a string like that? Or rather, I basically want everything after this. That should return an empty string. Yeah. and then I want to append, not append, okay, let's say result equal, hit that, and then result, basically want to add the input string, that's the other permutation. Okay, and then all other cases are basically this case plus the case of this case plus the case of hold on. So basically, like, all the permutations are going to be all possible permutations are all the other permutations plus a or like anything with the character that is missing, if that makes sense. So the base case is we've got an empty string. In that case, the only possible permutation is an empty string, right? So the next case, it should look a lot like problem 4, where basically, yeah. Subsets. I think it's worse than problem 4 though, or not worse, but like slightly more complicated than problem 4 because in a set, the order doesn't matter. But in a string, when you're talking about permutations, the order does matter. So you actually have more permutations. Although, okay, sorry. Something I just didn't realize is that I think when it says permutations without duplicates, I assume what it means is that, I didn't think of this before, but presumably all permutations have to contain all the characters. Yeah, so it's just like reordering the characters. Okay. So this is a different algorithm probably than I was originally thinking. So, all permutations. Let's see. The base case for this is assuming so let's just write out what it would look like for a really simple string. So if I have let's say I have like ABC, yeah. So permutations for ABC should be ABC, a CB, yeah, that's another one. CBA, CAB, BAC, B, C, A. Yeah? I think that's all of them. So how does this algorithm work? So for any string, all the possible permutations for that string are basically the first character plus all permutations for the substring, and then the same, but all permutations for the substring plus that character, right? Does that make sense? Okay, so it's a slice of one, blah, okay. Oh, I can't do it like this in Rust. Okay, so we'll go subperms equals, I need to make two calls. Let's say left equals, no, I only need to make one, sorry. So let sub permutations equal permutations without duplicates of s from 1 to the end. That, okay. And then I return, or rather I need to make a. Basically, there's a. Yeah. Okay. So I need to go. I need to basically copy this pattern here. Yeah. And then iterate over all the sub permutations and yada yada. Okay. So we'll say let character equal our item. Can't use the term character there. Equal S0. Yeah. And then basically do the same thing here. So iterate over that guy and then map it to a new basically a new vector here. So map, and then copying this pattern, clone these sub permutations, yeah. Let's new sub perms equal subperms.clone, and then for all these permutations, so basically add is I'm going to add the item at the beginning and the end. So I have to do this twice. If that's not confusing enough already. So it's actually like, I'm actually like exploding this, I'm exploding this, these subsets. What's the best way to do it? I think the best way is to just iterate over it twice. Yeah? Okay. Let's do insert like I did on the other one. So 0, and then it's going to be wait a minute. This should be a string. This returns a vector of strings. And this will be insert at 0, basically substring plus item like that. Okay. And the subperms. So do this, and then do this, and then do the same thing. So that first one is the like postfix, and then this will be prefix. So here we say item plus that. Oops, cargo test is not what I wanted. I need to return a thing. So I basically just want to return all of the previous sub-permutations plus all of these new ones, substrings. This one. And this one. And then return that. Oh, I'm not calling collect. 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 Cannot be built from specifying the type, right? What am I messing up there? Iter map. Format that. Collection of type cannot be built from the trait from iterator, blah, blah, blah. cdvac, st string is not implemented for. Oh. Okay. I understand why. S equal Rust string. It's because I'm trying to concatenate these strings. I want to concatenate it, but I want it to be to a new string. I'll just do a push, let s equal item dot clone, and then s dot push substring. Right? Or push string. And here I have to flip it around the other way, like this, yeah? Why can't I clone my string? Because that's not... I have to do string here, string. Test. Consider borrowing here. That's fine. What? Expected type. Indices are ranges of what? Consider borrowing here. Why is that not? This should just return a character, right? I just want an individual character. I need like dereference this. The type string cannot be indexed by integer. Okay, I think I'm doing it wrong. Get. I just want to get an individual character, right? Characters. Turn it into a slice. As string, as bytes. Rust sure slice. Yes. Primitive type. Characters. Get Returns a subslice. Bytes. Slice. Is that what I want? That's what I want. I want a slice. Structs. Rust for get character. Why is this so hard for me right now? I see. Just use an iterator. I get it. I get it. Okay, item, as characters, yada yada. All right. Whoops. Item, push. This is just one character. And this is just one character. I think I'm going in the right direction. Although it's still blowing up at collect. Collection of type vector string cannot be built from an iterator over elements of type std vector string. Am I insane, or does that not make any sense at all? I don't think it makes sense. This should work. Okay. Let me also just add the base case here. If is empty, no, if it's empty, return, yeah, otherwise, do this. Although I realize this is still not quite right, because really what I want to do, well, hold on. Let me try to understand why the trait from iterator is not implemented for, what the F? What is wrong with Google Chrome? Why is Google Chrome such a piece of garbage? You can collect and iterate over strings into a vector of strings. Collecting, oh, yeah, they're flat map. Okay. This is still not going to work. but I'm moving forward in the right direction. Trust me. I just have to make the compiler happy. Almost. All right. Can't borrow. Yeah, this should be mutable. All right, that compiles. Now let's think about this again. I still think this is wrong, and it's occurred to me why. It's because what I need to do is essentially insert the character at every possible position. Yeah. If that makes sense. Yeah, so for what I need to do here is iterate over all sub-permutations and then insert the character at every point. Right? So it's even worse than this. It's like, okay, I can simplify this a bit because I can delete that, and then I can go substrings. Here I say, so basically iterate over all sub-permutations. Let me just, and then for each sub-permutations, and then basically for each index in each like this. So enumerate over every character index and then insert that basically insert this character, blah blah blah, push. Okay, now I do need this mutable new sub-permutations. Let me just undo this. So for each index in substring, enumerate. Guys into here. It's basically the same as this, except I want to insert this character at each position in the substring, if that makes sense. So this is insert, index, character, and then I can just do push s, whatever, that's fine. That's confusing, super confusing to me right now. No iterator for characters, or just characters enumerate. There we go. All right. Let perms equal permutations without duplicates. S. It's a reference. And then print line. Rather, just do this. No. Do that. Nope, that's not working. Hold on. What am I doing wrong here? Oh, okay. I'm not handling the next base case. Yeah, the next possible base cases. So, the next base case is if string length is 1, then we'll just return a vector s. Yeah. And then if the length is equal to 2, then return a vector with. Alright, I guess I have 2 strings. String 1 is going to be equal to. What's the best way to do this? It's like format. This is a bit of a hack, but I'm not sure of a better way to do this. It's basically the first character and the second character. No, like, can I do this? Let me just try. Like that. And then string 2. It's basically these just flipped around. Or you know what? It's probably like, I can probably just do a vector of s and then s dot. So characters dot reverse, yes, correct. Does that work? No. This needs to be a real string. To string. Yeah, does it work? No, it doesn't work. It doesn't work because I should not be a yeah, okay, I see why. So I think at this point I just return these substrings, yeah? Like this. No, I'm missing something. Permutations. What am I missing here? Cargo format. Restart RLS. Actually, I think yeah, that's fine. So the case, why do we get, I'm messing, I've messed something up here. Not sure what. So subpermutations, so basically if there are 3 or more characters, then it should be flat map substring we should have ABC, and I've got ABC, ACB, ACB, CBA. No, it should be this one, and then CAB, CAB. I think I see where it's going wrong. So I'm missing why is BC getting repeated? So I'm calling this with substring that is like, hold on, let me just print out, let me put some debugging in here. So what is S? S is, all right, so it's called once with ABC and then once with BC. Oh, I see why. I think I see why. Yeah. So I'm cloning this and then I'm adding to it. I shouldn't be doing that. Shouldn't be doing that at all. What I should be doing is just making a new vector here. And then iterating. Yeah. 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 All right, that's better. It still doesn't work, but it's close. We're very close. This doesn't need to be mutable. That's true. Very, very close. All right, we're going to call it ABC and then BC. So that's right. So A gets added at every position except the last one. That is what's missing. So all I have to do here is go insert, basically do one more of these, 1, 2, 3, to insert at the end of the string. So it'll be, or rather I can just push. I can do item like that. Yeah. Boom. We did it. All right. That was kind of tricky. Not that hard. Makes sense now. I think we're good. So let's do this. Assert equal perms, or rather, let's just do this. I just need to fix the order of the arguments. These guys. And then we're there. Bingo. Sweet. Move that print. ABC, BAC, BCA, ACB, CAB, CBA. Let's add another test here. Let's change this to S1. And then Rust vec2set. Build hash set from vector. Hash set from iterator. Sweet. That's basically what I want. Okay, let's try a more complicated one. S2 equals A, B, C, D, E, F, G. And then we'll do let perms, or S2 perms equal permutations without duplicates. Should be S2. And then basically I'll say let S2 set equal and then assert that these are the same size. S2 perms dot length S2 set. No duplicates. Bingo. As well, check the size of that too. Assert equal S2.perms dot length should be equal to S2.length. What, length squared or something? Whoops. Did I do that right? No, I didn't do it right. Let's just hard code this. How do I do power? Pow. How do I use exponents? Rust exponent. How do I pow in Rust? You don't need the num crates. Just do derp.pow. Okay. Length.pow is 2.length. Expected you to 32, whatever. Okay, I don't know how to do math. Let's just hard code the number. All right, I think that's the right number. 5040 permutations. That sounds like a good amount of permutations. Let's run with it. Let's copy this into main. All right, let's add that. I forgot to add problem 6, or rather push it. I forgot to commit it and push it. So let's do that. I just did the wrong thing. So add problem 6. And then add problem 7. Yeah. Problem 7. Commit that. Push both of those to GitHub. All right. Beauty. Let's take a little break. little 5-minute break. We'll come back. We'll maybe do a couple more problems. All right. BRB. BRB LOL. Hello, I'm back. Microphone is unmuted. Hope my sound is still working. I think so. Let's do it. Let's continue. Continue with the problems. The computer code. Permutations without duplicates. All right. The next problem is permutations with duplicates. It says, focus please. Permutations, please focus camera. Focus on my hand. Yeah, there we go. Oh, lost it. Had it there for a sec. All right, good enough. Write a method to compute all permutations of a string whose characters are not necessarily unique. The list of permutations should not have... Oh, I see. So this is actually the exact same problem. It's just saying that the characters are not necessarily unique. So basically just going to copy the last problem and change the tests because the code is identical otherwise. Okay. Copy problem 7, paste problem 8, and let's just delete that test case. Don't need it. Let's do ABB. Okay. And basically just anywhere you see C, replace it with B. Excuse me, I burped. Cargo test. That's it. Problem 8 is done. I can remove this because I'm not using that. Alright, add problem 8, git commit, problem 8, chapter 8, problem 8. Yeah? Push that up to GitHub. Let's check to make sure that the build is still working, passing. Sure it is, maybe. Build history, yeah. All green, looks good. By the way, for anyone who's new to the stream, either just joining in, maybe you're watching the recorded videos, you're looking for a place to start or figure out what's going on, you don't know, you can always go to my GitHub profile /cracking the coding interview Rust and look at the code. All of the code is up on here, as well as a link to all of the past videos. If you want to watch any of them, there it is. Check them out. If you want to suggest changes as well, you know, feel free to open a PR or whatever. The only thing I ask is that you don't solve the problems I haven't solved yet, and leave that to me. Although feel free to solve them on your own. I want to do them on the stream here. So that's that. All right, moving on. What's the next problem? What is the next problem? Problem 8, chapter 8, problem 9. Parentheses. I already know how to solve this one. It says parentheses. Please be focused. Implement an algorithm to print all valid, in other words, properly opened and closed combinations of n pairs of parentheses. Okay. So there's an example there. If your input is 3, then it should print out those guys. All right, this is really just another take or another variation on the last problem, but with a little a tweak, a little new perspective. Oh, I also need to change. Just occurred to me that the last problem, yeah, I need to change the name on it. It should be. This one should be Permutations with dupes. I'm just changing the test name, even though it's literally the exact same code, but whatever. Let me just change that. Fix chapter 8 P08 name. Yeah, whatever, good enough. Okay, let's copy problem 8 and paste problem 9. Let's close these other ones. Problem 7, problem 8. Whoops, I just closed problem 9. Okay. So what is this problem called? It's called parens. Test parens, no T. And I'm just going to delete all the old code, start fresh. All right, so we'll call this generate parens, no T, or let's say get parens, whatever. It takes in a number, and let's just say I32. Let's make it unsigned, and it returns a. We'll just say a list of strings. Okay. So let's start by handling the base cases. So if n is equal to 0, then we just return an empty vector like that. Else if n is equal to 1, then 1 should just return a vector like this. Basically 1 open, 1 close. Yeah? Okay. And then the rest of this problem is very much like the previous one. So much that I'm also just going to copy this block of code here and start filling it out. Just basically put that port the algorithm over here. So it's going to be n-1. Let's start there. And let's change this to subparens, yada yada. Let's change this to new subparens. All right. So how does this work? Basically, for all For all combinations of parentheses, so the base case is you add a parenthesis, or you add an opening parentheses at the beginning and a closed parentheses at the end. Okay, that's one case. Another case is you add open close at the beginning and or open close at the end. All right, let's handle those. So let's do that. Delete all this because it's not really what I want. Yeah, okay, so basically we're gonna have three parens. Preparens is going to be, let's do basically like this, and then preparens. Actually, there's probably an easier way to do this using string format. Dirt, and then substring. Preparens. And then post parens, let's call it. Or actually, I can just push this directly. Yeah, okay, that's better. Push that. So that's pre. This is going to be post. And then there's only one other case, which is like this, basically wrapped like that. Format macro. Sorry, that should have been string from. I did it wrong, but this will work. This needs to have a toString. Whoops. Man, I suck at typing. All right. All of that compiles. Beautiful. Now, let's test it. Should be pretty simple. We should just say parens, let parens equal, or I don't even need to do that. Let's do assert equal, get parens 1. This should just give me a vector like this. Might as well test for 0. Sure. Empty vector. Let me just change this to true, and then is empty. Okay, there we go. All right, that works. Now we'll do 2. So for 2, this is going to get a little messy. So there's this case, and there's this case. That's it, basically. Oh, had my brackets in the wrong place. Oh dear. Oh, I have a duplicate. I see. So I should really have one more base case in here, I think, which is just going to be if n equals 2. So in the case of 2, there's only 2 possible cases. Yeah. Like this. There we go. Change the order of them. There we go. And then now 3 should work. Okay, the params 3. There's going to be that case, there's going to be this case, there's going to be this case, and then there's going to be, what am I missing? This case, I think I need one more. Or is that it? That might be it. I need to change this number to a 3. Okay, so my algorithm doesn't work. It's returning duplicate cases here. Why is that happening? Why is that happening? What did I do wrong? One moment while I think about this. Hold on, what is it returning? It looks kind of right. I'm just returning this case twice. Why is that happening? Zero, 1, 2, 3. Hold on, look at the book. 1, 2, 3. There's 5 cases. I'm missing one here as well in my test. What am I missing? Doop, doop, which is the one I'm missing? It's really hard to read parentheses like that. So open. There's only so many different ways you can do these. So open, close, open, close. And then open, open, close. Open, close, close. Which is the case I'm missing? What is going on in my brain? Oh, yeah, of course, I see. It's this one. Yes. Okay. So why do I have the extra case? Basically, this one is duplicated. Why is that one being duplicated? Please help me understand. So get parens for n minus 1, which will be 2. So it's going to return this guy and this guy. And so I see why. I see why it gets duplicated. Yeah. Let me just test something here. That should be wrong. Yeah, it is wrong. Basically, I need to ignore the case where, you know, these two are equal. What's the best way to do that? It only happens if, yeah, it only happens if only happens in a particular case. So I think probably the way to do it is to just check in here, but I'll just, this isn't great, but I'm not sure if there's a better way right now. So I'll just say if if new basically if these are not equal, if these are not equal, add that substring. I don't know if there's a better way to do that. Sweet. Okay, the order is wrong, but I believe that works. So let me fix the order. Is that right? Boom. All right, good enough. So this is kind of ugly, but let me see. Yeah, I don't think there is actually a better way to do that. Because this is just like one particular special case. Excuse me. Yeah, this is good enough. Doesn't have to be perfect. I'll just add a comment there about how this is basically a special case. Yeah. All right, that's it, problem 9. Let's add it, git add. Problem 9, check it in, push it up. It's gonna run the build. Oh dear, I should run Clippy. I think Clippy's gonna fail. I forgot to check. Yeah, it is. Because I'm not calling this in main. So let's put that into main. Let's fix the formatting, and let's say fix Clippy warnings. There we go, okay. Fix that. Moving on, next problem. Next problem. What is the next problem? Next problem is called paint fill. Right there. Please focus. All right. Implement the paint fill function that one might see on many image editing programs. That is, given a screen represented by a two-dimensional array of colors, a point, and a new color, fill in the surrounding area until the image changes from the original color. Okay. That makes sense. So you have a two-dimensional array of colors and you want to fill around some point. All right, let's copy problem 9, paste. We're on problem 10. It's called paint fill. Test paint fill. Test paint fill. All right, so function paint fill, it's going to take in a point, let's just say X, we'll just go with X and Y, and then a canvas, which we'll just say is a vector of I32, of a two-dimensional vector of, let's just say I32s. And this will be a mutable vector. Beautiful. So the algorithm is pretty simple. This is not too different from, for example, some of the stuff we did in the Minesweeper game, where basically you have some point somewhere, and you need to check the adjacent points, see if they are the same color. And then if they are, they would get filled. It's the same, whatever. I think you'll find that the paint fill algorithms in like any real image processing software, like a Photoshop or something, where they can, they're a little more sophisticated than that, but this is a simple problem. So. Okay, So let's handle the simplest case, which is basically you need to get the color of the current pixel. So, also need to specify a new color here, new color, and that'll just be an I32. Okay, so let's current color equal canvas, get the color at X and Y. Yeah. Let me restart RLS again. Current color. Okay, so get the current color at the current point. Easy peasy. And then change the color, current point. So canvas, X, Y. Change this to the new color. Let's see if that compiles. It should. Yeah. So that's the basic operation. You have a point in the canvas, change the color. Easy peasy. So the next thing to do is, so for, we'll say X offset in, now we're going to go from -1 to 1, and then for Y offset in -1 to 1. So we're going to look around the current point. So let's skip, we'll say if X offset equals 0 and Y offset equals 0, so skip the current point. Don't need to do anything for that point, right? Okay. So why is Vim blown up? Okay, so we'll say let X equal X plus X offset. Now X is unsigned and X offset is signed, so we have to cast as this to a signed integer. We'll say I64, whatever, and then do this, and then cast it back to a usize. Let's do that, and then Y, same, Y is I64 plus Y offset. Okay, there we go. That compiles. So we have our X and our Y. So we'll say if X is greater than 0, and X is less than canvas dot length. Do this. Let's also check that if X is greater than 0 and X is less than canvas dot length, and Y is greater than 0 and Y is less than canvas 0 dot length. Alright, that's to check the bounds, make sure that we are where we need to be. Okay, and then here we'll say if canvas X, Y is equal to current color. I'm going to rename current color to old color, or previous color. So if it's the same color, then apply the paint fill. X, Y, canvas, new color. That's it. That's the algorithm. I believe we're done. Let's test it. Okay. So let's make a canvas. Let canvas equal a vector of, let's make it a really simple, like 5 by 5. Can we do that? Yeah. So there's 5. 1, 2, 3, 4, 5. All right. And let's build a wall. Okay. Well, let's say we want to fill at 0, 0. Paint fill at 0, 0. This canvas, new color 2, something like that. This should be mutable. 0, 0, new color 2. Okay. Then our canvas should become assert equal, should be this, but these are all going to switch to 2. Like that. Assert equal, canvas. Something like that. Types differ in mutability. Oh boy. Oh boy, oh boy, oh boy. Didn't quite work. Something is wrong. What went wrong? Let's figure out what went wrong. Alright, so I'm filling at 0. I'm filling with the color 2. Alright. So what are we getting here? So I'm getting 2, 0, blah, blah. So yeah, it's not working. This statement can be collapsed. Oh, yeah, that's true. So it's filling the first color, but it's not filling the other ones. So it's like almost correct. It's just not correct. So if x offset is 0 and y offset is 0, then skip it. Don't care. Otherwise, x is equal to x as I64 plus y offset. Okay. Oh, this should be greater than or equal to 0. Yeah, got it. Got it, got it, got it, got it, got it, got it. I think that was it, but it looks like it's still failing. However, yeah, it is still broken. Beautiful, beautiful, beautiful. This is amazing. Why do I have... Comparison is useless due to type limits. Interesting. Interesting, interesting. That's a good point. So let's just remove that. It still doesn't work. Okay. Oh, yeah, it's because this needs to be an inclusive range like that. Okay. I think we got it. I think we got it. Boom! We got it. Woo-wee! Good work, team. What a proud moment. Proud moment in computers. I'm just one step away from winning the Turing Award. someday. Just kidding. Just kidding. Okay. They would never let me go to any kind of award ceremony thing of any type. That'll just never happen in my life. Oh, I should check Clippy warnings. All right, I think we're all set. Problem 10. Let's push that up to GitHub, and let's see what's next. What is next in the book? Go into the book. To the book. Problem 11. Oh boy, this is a good one. Seen this one a few times in my life. Imagine everyone has. Given an infinite number of quarters, dimes, nickels, and pennies. It's time to get rid of the penny, by the way. Write code to calculate the number of ways of representing n cents. Number of different ways to represent n cents. Infinite number of coins. All right, this is pretty easy. Honestly, all these problems are like basically the same ideas. They're just variations on the exact same concepts. So they do become a bit tiring after a while, to be honest. Okay, let's delete this, get a fresh canvas. Pun intended. Paint, what was this one called? It's just called coins. Coins. All right, so number of different what is it? Sorry, I forget what the problem is asking already. Given an infinite number of coins, calculate the number of ways of representing n cents, right? Okay. So, ways of number of what's the right word? Number of permutations is not the right word. Patterns is not the right word. What is the, it's basically like, let's go to a dictionary. Permutation. So the difference between it's basically like actually change is a good word. Let's just say make change. And we'll just use a use size, and then this is just going to return I64. Let's use I64. Okay. It should be U64. You can't really have negative. Okay, test coins, make change. So let's see. If n is less than 5, so if n is less than 5, it's very easy. The answer is n, right? If you have, or not n, the answer is 1, sorry. Right? So if you have, 4 cents, there's only one way to represent 4 cents, with 4 pennies. If you have 3 cents, same. If you have 0, it's still 1. There's only one way to represent 0, and that's no coins, right? Okay. So the next option is if n is less than 10, yeah, you basically have the number of different ways that you can represent say 9 is going to be or any number less than 9 and greater than or equal to 5 is 2, right? Because you can either have 1 nickel and n pennies, or I mean that's it, or n pennies, yeah, right? Those are your only options. Okay. Okay, and if n is less than 25, then, so if n is less than 25, then it's going to be all of the ways that you can represent with dimes, basically, which is, so for 25 you could have 2 dimes and 1 nickel, yeah? So you could have, you could basically have 10 plus 10 plus 5, you could have 10 plus 10 plus 1 penny 5 times, sorry, 4. All right, less than 25, yeah, that's right, okay. And you could have 10 plus 2 times 5 plus 1 times 4. You could have 4 times 5 plus 1 times 4. Right? 3 different ways. This would be 1 times n. This would be 1 times n, or 5. Okay. Times n. Like that, right? 1, 2, 3. Right, and then the last case. Not the last case. Is it the last case? Yeah, else. I think this is the last case. So, a number of ways you can represent any number above, or that's at least 25, is going to be basically 1 plus, so 1, which is where you have a quarter. I've got 1 quarter. Yeah. Plus all the different ways that I can so it's that way plus all the different ways that I can make change for n minus 25. Okay. And then yeah, that's it, right? No, it's more than that. Hold on, because it's also these guys. So also the base cases. I think I can do this simpler, but hold on, bear with me. So it's gonna be 1 plus all the ways I can make change for n without a quarter. Yeah. And then plus all the different ways I can make change for n minus a dime, minus a nickel, minus a penny, right? Hold on. This doesn't work yet. I should make this, I think I can simplify this a great deal. So I think if I make this signed, then it makes this a little easier. So if I do this, I say if n is less than 0, then less than 0. Okay. So I think it should just be 1 plus all of these. Yeah? Alright, that compiles. Let's test it. So the base cases are easy. I don't really need to worry about that. Let's do it for the other cases. All right, so 26. How many different ways should I be able to make change for 26? So I can have so for 26 cents, I can have a quarter plus a penny, yeah? Or I can have a dime plus, so I can have 2 dimes. That's 20 cents plus a nickel plus a penny, okay? Or I can have 2 dimes plus 6 pennies, or I can have a dime plus 2 nickels. This is gonna take a really long time. Okay, I don't want to do this all. I think it'll be a lot. I don't know, like 10 or something. Let's see. Let's just run the test. See what we get here. 19. Yeah, that sounds about right. Must be right. How do I test this without having to actually test it? Make change. No, I don't want to cheat. I'm pretty sure it's right, but I don't want to cheat. Let me just look at my algorithm. So there are 2, yeah, so if you've got less than 5 cents, if you've got less than 0 cents, you can't make change at all. You can't make change for any value less than that. Yeah. I'm not sure this is right though. I kind of feel like this should just be. So basically, yeah, all the ways that you can make change for any number is all the ways that you can make change for that number minus each of the denominations, right? I think that is right. Is my sound still on? Can people hear me? I think so. Looks like it's still working. Yeah. Yeah, it's working. It's working. uh, 19. Is that right? Let me try some other. Well, all these lower numbers, I already know what the answer is, so it's easy. Any number below 26 basically is meaningless. Or even 25. Let's try 25. So 27 should just be 20, because there's only one additional way, right? So I add 1 penny. Sorry, 11. Is that right? 11 different ways to make change for 25. Sounds about right. 27. I don't think that's right. I think it should be like this. No, I didn't think about it. That's not right. Hold on. 10, 11. How many different ways can I make change for 25? Let me just make sure that that case works. So for 25, I can have 25 times 1 penny. Or I can have 20 pennies plus 1 nickel. Or I can have 15 pennies plus 2 nickels. Or I can have 10 pennies plus 3 nickels. Or I can have 5 pennies plus 4 nickels. Or I can have 5 nickels, right? So that's all of those different ways. I can also have 15 pennies time plus 1 dime. I can also have 10 pennies plus a dime plus a nickel. I can also have 5 pennies plus a dime plus 2 nickels. This is taking way too long to figure out. What's the correct number? Hold on. Let me solve this for like the simpler case and then verify that I did that right, and then I'll come back. So forget about quarters. Let's do pennies, nickels, and dimes. All right, so this should be 1 plus make change n minus 1 plus make change n hold on. left. Yeah, so that is right. Okay, 10 and then 11 should basically just be one more than that. Yeah, okay, let's go up to 15. 15 should be like 5, right? 8. That doesn't seem right. So to do 15, for 15 I can do 15 pennies. I can do 3 dimes. I can do 5 pennies plus, sorry, nickel, 2 nickels. I can do 10 pennies plus 1 nickel. I can do 5 pennies plus 1 dime. I can do 2 dimes plus 1 nickel, right? That's all it counts. 1, 2, 3, 4, 5, 6. That's for 15. That's not right. Right? 6. I think it should be like this. Comment these out. It should be n minus 10 plus. Is this right? No, hold on. So for 15, so like all the ways that I can make change for these numbers should work. So all the ways that I can make change for 10 is equal to no, this doesn't make sense. 1 plus what am I doing? I'm like getting super lost in my thoughts here. I think I just really suck at programming. That's what it is. Could just be that I've been staring at the screen too long. All right, make change. All the ways that I can make change for the base cases are simple. All right, if n is less than 0, can't make change, 0. If n is less than 5, then I can only make change one way. If I have less than 5 cents, there's only one way to make change, that's with pennies. If I have less than 10 cents, there's only 2 ways to make change. Okay, this all makes sense. Okay. Now if I have 10 cents or more, so if I have 10 cents, I have all the ways to make change with 10 cents, plus all the ways to make change for 9 cents. And all the ways to make a change. Yeah, yada yada, okay. I think this is right. Yeah? No. I think it's because I'm duplicating the math here. I think it should just be simplified. No, that doesn't work. Why am I doing that wrong? N minus 1. That is a given, right? So how many ways can I make change for 10 cents? So I can have 10 pennies, I can have 5 pennies plus 1 nickel, I can have 2 nickels, or I can have 1 dime. Yeah, that is 4. Alright. I think my brain's working better now. Got it. Alright, if I add 1 more, then, so it's going to be, I can either have 10 pennies plus 1, or I can have plus 5, or I can have times 5 plus 1, or I can have 10 plus 1. So that should still be 4. 34. Yeah, that's fine. Okay, this is returning 7. Is that right? Should this be 7? Let's check it. 1, 2, 3, 4, 5, 6. So if I have 15 cents, I can have 15 pennies, I can have 3 nickels, I can have 5 pennies and 2 nickels, I can have 10 pennies or 1 nickel, I can have 5 pennies, 1 dime, I can have 2 dimes or 1 nickel. Where does the 7th one come from? What am I missing? What am I missing? Do we have 5 pennies? Oh yeah. Oh yeah. No. 5 pennies, 1 dime. Is there a 7th case? I think this one here is wrong. And I think it's because I need this case. Also if n is less than 10, 2, right? That breaks it. Oh, it should be This should be 1 plus. Test is passing. Is that right? 1, 2, 3, 4, 5, 6. Can't be right because I'm missing a case here, right? So I can have 15 pennies, I can have 3 nickels, I can have 5 pennies and 2 nickels, I can have 10 pennies, 1 nickel, I can have 5 pennies and 1 dime, I can have 10 pennies and 1 nickel. What am I missing? I think there should be a penny plus, or sorry, a dime plus a nickel. What am I missing? Why is that 7? I feel this value here is messing it up. I don't know why this algorithm has been so hard for me right now. This should not be that hard. What am I doing wrong? I know I've done this problem before, like many times. For whatever reason, I'm unable to do it right now. I don't want to cheat. I want to solve it. I want to solve it. So, all the ways that you can make change for any denomination is equal to all the ways that you can make change for all of the other possibilities. I think like the fact that I'm ignoring pennies here, yeah, that seems wrong, right? But then this blows up. Because pennies don't really matter, do they? So if n is less than 10, yada yada. It's less than 25, it's 3, right? This breaks. Let me check. So it's breaking on the make change for 10, which has 4 possible ways, right? I can either have 10 pennies, or I can have 5 pennies and a nickel, or I can have 2 nickels, or I can have a dime. That's 4 distinct ways. That should be 4. Here it returns 3. Oh. 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 I think this should be 1 plus these values. Right? Oh, these numbers are wrong. This should be 4. Whoops. Okay. And then 11 fails. Right? Line 30. Oh no. Yeah, here. Left 4. No. 4 is not right. 7. 1, 2, 3, 4, 5, 6. It should be 6. Am I right? You know, 15 pennies. So I think this should be 1 plus. By the way, but let's work. 7. So why does that not work? Why does that not work? Why is it 4? It's not 4. I think I'm thinking about this wrong. So let's think about the end case. So basically, for any value, for any amount of money that I have, I would subtract the denomination, the largest denomination. No, that doesn't work. Never mind. I'm not trying to find the optimal change. We're just trying to find the number of different ways that you can make change, which for any given number should just be the number of ways you can make change for that number plus the number of different ways you can make change for one less than that number, right? Yeah. That makes way more sense. Okay. Number of ways you can make change for any given number is all the number of ways that you can make change for No, that doesn't make sense. So you only add new ways to make change for a number. You only add new ways to make change for any given number if you add a certain amount, right? So like, if you add 1 cent to the number of cents, it doesn't necessarily change the number of ways you can make change. Because the number of ways that you can make change for, 1 cent, 1, 2, 3, 4 is all the same. Number of ways that you can make change for 5, 6, 7, 8, 9 is all the same. So this can't be true. So the number of ways, number of ways that you can make change for whatever should be equal to number of ways you can make change for n minus 1 plus blah 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 plus, right? And this is the only thing that makes sense. 10, 20, 25. That does not work. 4 is not the right answer for that, for 15. There should be 6. Why does this not come out? What is wrong with my brain? All right, I'm thinking too hard about this. Make change problem. Change making problem. Oh yeah, I remember. I know why. Got it. I remember now. Basically, the trick here is to take the minimum, the smaller of these results. Yeah. Coin change problem. Here it is on hacker rank. If I were to rank myself as a hacker, I'd get a 0 right now. Yeah. Turns the count of ways that we can sum S0 to get some n. If n is 0, then there is one solution. Do not include any coin. Get lost. If n is less than 0, then no solution exists. Okay, yeah. Looks pretty similar to what I have. If there are no coins and n is greater than 0, then no solution exists. That is not quite the same problem. These are slightly different, actually. But yeah. So basically, I'm going to look at that problem again. Count of ways we can sum coins to get some n. Okay, so S are the coins. 1, 2, 3. Right. n is less than 0, no solution. If there are no coins, then so the base case is just return 1 in that one, right? And then they're just doing, what are they doing here? Count of m. What is m? M minus 1. This makes sense to me. Solution does not make sense. Greedy method. This is the solution here. I just don't like this code. This uses a matrix to keep track of the optimal solutions to the subproblems. I don't want to do it this way. Alright. I'm kind of stuck on this problem. Let's see if I can make my brain work for a few more minutes here. I just have to squeeze out a little bit of brain. So I don't know why I'm struggling so much on this problem. What did I just change? 21. No, that's wrong. Okay, this should be 4. So so for any given value, all ways that you can make a change for that value is equal to, so it's basically like number of ways. So if I have $1, number of ways I can make change for $1 is equal to all the ways I can make change for $1 minus $0.25. I don't know, I'm thinking about this wrong. Totally totally thinking about this wrong. Why am I why am I struggling so much with this problem? Why am I struggling? All right, I'm gonna take a little 5-minute break right now. I will be back. All right, I'm back. I'm gonna try to solve this. I'm finding this problem hard right now. I think my brain is low on glucose or something. This really shouldn't be that hard. So let's just think through this again. If I have left less than 5 cents, I can only make change one way. if I have less than 10 cents, I can make change 2 ways. If I have less than 25 cents, then I can make change, what, 4 ways? Yeah? Okay. So, number of ways that I can make change for all other denominations should be number of ways I can make change for n minus 1, or rather should be the min, right? Must min so it should be the smaller of number of ways I can make change for n minus 1. Is it smaller or is it hip up? It'd be the max, right? Number of ways I can make change for n minus 1. And the number of ways I can make change for n minus 5 and so on, right? Is that right? n minus 25 and that. Rust vector max. There's got to be a better way to get the max. There's a max on iter. Max. Oh, this will work. Let's do this. Vec. don't want. How do I? All right. This is still wrong. Let's look at the book. Page 362. Look at the book. Ah, yes. I see now. A mistake I'm making. I understand why I'm doing this wrong. I understand. So, yeah. No, we're gonna go to the park in a little bit. Let me solve this problem first. So a better way to solve this would be, yeah. Okay, I think I can make this better. I should have amount. Let's just change this for 1. No. I'm looking at the book solution right now. Just seeing how they did it in the book. Where is it? I see why I'm doing it wrong now. See? I see my mistake. We'll go to the park in a bit. Doja's crying. She wants to go to the park. We will go to the park in a little bit. Okay? Promise. Promise we'll go. So the book proposes memoizing this as well. No, no crying. So I think I'm basically just going to translate the book solution into Rust here and do it the way it's done in the book. No. So this would be like 25, 10, 5, 1. Right, these are our denominations, but you just wait. I'm gonna finish this up real quick and then we will go to the park. Alright, pup? Doja's having a freak out. She wants to go outside. We're gonna go out very soon. Alright? You just relax, pup. Promise. Promise we will go. Alright. I'm going to just translate the bulk solution. So basically if the index is past the end of the denominations, return 1, otherwise let amount equal denoms index. So this is the denomination amount. Yeah. And then for I in a range up to no, this doesn't work. Hey, pup. Yeah, I see what they're doing. Hey, pup. What you doing? She's just got the goofiest face right now. So this should be the amount divided by I up to, no, this doesn't work. The way that the code is written in the book is kind of confusing, so let's do this a different way. Let mutable I equals 0 while I is less than. We're or equal to, sorry, well, I times the denomination amount is less than or equal to the amount equals 1, and then keep up. Make change is going to be amount minus times the denominator. Hip hop. Please relax. The next denomination, and then panicked. Line 27. Auto format. That can't be right. 19 ways to make change for 10 cents? No, that's not right. That is not right. What did I do wrong here? It should be greater than or equal to. There we go. There we go. All right. I did it. I had to cheat, I had to copy from the book, but I need to take Doge out, and my brain is just, it's not working good right now, so. Now this is not exactly the most optimal solution, because basically this function call happens like this. This should be memoized, this call, because it's going to happen lots and lots of times, but I'm not going to fix that right now. Okay. I'm going to add this problem 11. Oops, I should check Clippy. Git commit a amend reset author. All right, I'm pushing that up. And I'm going to call it a day. Call it a day. End of stream. That problem is tricky for my brain right now, although I see now that it's pretty straightforward if you do it the way that the book tells you to do it. Anyway, thanks for watching. Thanks for tuning in. I hope you get some value out of this. Maybe not from that last problem, but hopefully from some of the other problems. I hope you enjoyed it. If you want to tweet at me, send me a message, say hello, whatever, feel free. Thanks for watching. I hope you drop in next time. If you're watching the recording, then I hope that's good too. Catch you next time. Bye for now.